Hello, ladies and gentlemen. Thank you for standing by. Welcome to this ASM webinar, Vacuum for Your Industrial Process, Creating, Measuring, and Maintaining for Optimal Performance. I'm Vicki Burt, editor with ASM International, and we're glad you could join us today. Today's presentation is part of the ASM webinar series designed to provide information you can apply to improve quality, efficiency, and performance. This webinar series supports the needs of our members, customers, and the materials community at large. The series also supports the outreach needs of the leading corporate supporters of ASM and its affiliate societies. The sponsor of today's webinar is Agilent Technologies, headquartered in Santa Clara, California, with offices throughout the world. Agilent is a leader in instrumentation for the life sciences, diagnostics, physics research, and applied chemical, energy, and materials markets. The company provides laboratories and manufacturers worldwide with instruments, services, consumables, applications, and expertise, enabling customers to gain the insights they seek. Agilent's expertise and trusted collaboration give them the highest confidence in our solutions. The company's 11,000 employees serve customers in more than 100 countries with products and services that make a real difference in the lives of people everywhere. More information can be found online at the address on your screen. We're proud to have Agilent Technologies on board for today's webinar. Before we begin, let me mention a few housekeeping issues. If you're having technical difficulties in joining the WebEx session, dial 877-582-7011. All participants will be in a listen-only mode during the presentation. Feel free to submit written questions at any time by using the question window. We'll answer as many questions as we can at the end of the webinar. We're proud to host today's webinar. For over 100 years, ASM International has served the materials community by providing scientific, engineering, and technical information, as well as education, networking, and professional development. Advanced Materials and Processes is ASM's flagship technical magazine. It provides information about leading-edge developments and trends in engineering materials and the methods used to select, process, fabricate, test, and characterize them. The magazine also covers emerging technologies such as nanotechnology, additive manufacturing, and management topics of interest to scientists and engineers. With that, I'd like to introduce today's panelists, John Screech, John McLaren, Lydia Oyama, and Dave McCarthy. John Screech, Senior Applications Engineer. When he isn't delivering technology training, John works with customers to define solutions for their challenging applications. John McLaren, Marketing Manager, Leak Detection. Since joining Agilent in 1995, John has held various sales management and marketing positions and has over 25 years of leak detection experience. Lydia Oyama, Product Marketing Manager, Diffusion Pumps and Vacuum Controls. Lydia manages Agilent's extensive line of diffusion pumps and vacuum controls, including vacuum gauges, controllers, and components. Dave McCarthy, Business Development Manager, Vacuum. Dave is currently the Channel and Business Development Manager for the industrial market. He has worked in various product marketing, sales, and sales management roles at Varian Agilent over the past 23 years. And now, I'll let John Screech get us started.
Thanks very much, Vicki, and welcome to this webinar. I hope we can give you some information. We've got a lot of slides lined up, and we've got a very talented group of panelists here, and I hope we can really help you out in terms of giving you information that can help your process and help you troubleshoot, and even in some cases, maybe design industrial vacuum systems. So let's jump right in. So quickly, just to get started, we'll go right back to the start. When we talk about vacuum, we're talking about anything, anytime we have a pressure less than 1 atmosphere in a vessel. So anytime we can decrease the density of gas particles below what we would see at atmospheric pressure, we can refer to that as a system under vacuum. One of the ways to conceive vacuum is it's a force per unit area. So the most obvious example of that is if we use the traditional units of PSI or pounds per square inch, we can really think about a force of 1 pound acting on a surface area of 1 inch. These are just in the bottom right of your screen. You'll see some different gauge units. One of the things that we encounter in industrial at our industrial customers is a wide variety of units that those customers will use. Whereas in the, let's say, the scientific markets, we typically use torr or millibar. We see all kinds of things in the industrial scale. We see pounds per square inch, inches of mercury, and microns is another popular one. So I apologize if we're going to mix units up a little bit in this presentation. So we'll see if we can't stick to one unit, let's say. So first of all, why do we need vacuum? I always say when I teach the classes, no one's doing vacuum for the sake of doing vacuum anymore. We're all using vacuum, particularly in industry, for a particular purpose. So there's something that we want to achieve that requires a vacuum environment. Particularly in the industrial space, it's about creating and maintaining a clean chemical environment. We're somehow altering the chemical environment that we're going to put our parts into. Obvious example would be surface coating, where we're trying to maintain a clean surface to do a deposition onto, whether that's a processing, let's say, of something like a roll coater with potato chip bags, or something like a semiconductor process where we're going to deposit in very thin, almost nano layers onto a surface. And really the idea of having a clean surface there is to avoid particularly having water contamination on that surface. As you can imagine, every surface inside a vacuum chamber is coated with water molecules. And one of the ways to reduce that surface layer of water is to put a system under vacuum. For our particle accelerator and high energy physics customers, they're more concerned about moving particles over a long distance. Anytime we want a particle to travel without it being knocked off course through collisions with background gas molecules, we need to reduce again the particle density inside our vacuum vessel. Finally, a lot of industrial processes require very high voltages in very close proximity. And of course, if we didn't get rid of the background gas there, that high voltage would simply discharge or create an arc across those positive and negative terminals. One last reason for requiring vacuum, and John McLaren will speak in some detail about this later, is that when we're doing leak detection, so we want to try and use, let's say, a helium mass spec leak detector to determine what the source of vacuum leaks are in our vessel, we need to create the conditions for flow. So gas will always flow from an area of high pressure to an area of low pressure. And we try and create that differential pressure in order to get helium from outside the vacuum system towards our detector, or in the case of a pressurized vessel, from inside the chamber going outside through our sniffer probe to our detector. So that's kind of a unique condition that we require vacuum for in the leak detection business. So I've mentioned a little bit about some gas load sources. This would be sort of an illustration of an industrial vacuum system. So typically we have some sort of process gas shown up in the upper right of the graphic here. And then we have some of the potential sources of vacuum leaks or of gas sources that we need to deal with our vacuum system. So when we think about desorption, as I mentioned a little bit about in the semiconductor processes, trying to get water off surfaces. Diffusion is a similar process, but we really refer to diffusion as coming out from bulk materials. So whether it's the interior of the vacuum chamber itself or any of the material that we have inside the chamber that could be somewhat porous and could be emitting gases. When we think about the industrial world though, permeation, that the graphic that just disappeared, that really shows up really at much lower pressures than are typical for industrial processes, something around 10 to the minus 8, 10 to the minus 9, where we're starting to be concerned about whether we have O-rings that have some permeability for helium, for example, or the permeability of our vacuum chamber and its ability to emit hydrogen. Those are typical problems that show up at much lower pressures. So we can kind of get rid of that. Backstreaming, we're going to talk about a little bit when we get to our talk on vapor jet or diffusion pumps. However, vacuum as a source of gas load in industrial processes is generally not a problem. We're not really approaching the compression limit of our high vacuum pumps. So we can kind of get rid of that. And these are really the 5 things that we're going to be chasing, or the obstacles we're going to try and overcome as we get our industrial vacuum system down to its base pressure. Diffusion, a little bit less of a factor, I guess, because that typically comes in at pressures below 10 to the minus 4, 10 to the minus 5 torr, something in that range. And a lot of industrial processes have it at pressures closer to atmosphere than that. So for a lot of our customers, diffusion is less of a concern. And we're really looking at real and virtual leaks, desorption, and our process gas as being the obstacles we need to overcome. So this is a nice graphic. I like just kind of shows some of the range of vacuum processes. Again, we're using torr on this scale, and we can see where some of our industrial processes like freeze drying, roll coating, and heat treatment show up in this vacuum spectrum. So because the industrial processes cover all the way from rough vacuum through to high vacuum, we're going to need to talk a little bit about how we create and measure rough vacuum pressures and also high vacuum pressures as well. One of the things that we need to consider is that the different behavior of gases, really the boundary between rough vacuum and high vacuum can really be considered the transition point between particles moving in viscous flow and particles moving in molecular flow. So any of the engineers in the audience, you'll be familiar with viscous flow. So a lot of calculations are done in college and university about how, for example, water moves through a tube, and the mathematics on viscous flow processes are fairly well understood. And we have a solid series of mathematics and formulas that we can do a lot of calculations for the behavior of fluids. And we treat gas as a fluid in this sense in viscous flow. When we get into high vacuum, we need to consider the particles are behaving in molecular flow. So this is an old Pong video game graphic with a background superimposed it here on the left of your screen. In this sense, the particles are moving completely independently. They have very little interaction with each other and are only reaction with the chamber. And for this reason, you're going to see that when we have our high vacuum pumps, we want to connect those up to the vacuum chamber with as large an opening as possible and have as little restriction as absolutely possible between our vacuum chamber and our high vacuum pumping system, because those particles are behaving in molecular flow. The boundary in between rough vacuum and high vacuum is a little bit messy, and a lot of the formulas and our approximations for the behavior of those gases don't really hold true. So a lot of times when we're trying to model systems in that transition point, let's say somewhere between 1 millitorr and 100 millitorr, we really need to go out and do those experiments empirically to understand exactly what's going to happen and what size pump might be required to achieve a particular vacuum pressure in that transition region between rough vacuum and high vacuum. So we're going to talk about one of our biggest enemies in the vacuum world, and that's conductance. So conductance can be thought of as the amount of gas or the amount of fluid we could flow through a tube. And really we refer to when we talk about conductance, generally we're talking about its effect on restricting our vacuum pump's performance. So we need to have some formulas. A lot of you will have rough vacuum systems connected up to a vacuum chamber through some length of tubing. And in order to calculate what the restriction or what the cost of that in terms of impacting our pump speed would be, you need to use this formula for conductance here. So shown just below the illustration of the pipe here. When we have multiple tubings or different tubings connected to different lengths of tubings at different diameters, we can use that 1 over the total conductance is 1 over conductance 1 plus 1 over conductance 2, et cetera, et cetera. Just for example, I've shown some conductance values that I've calculated out for tubing at different diameters. We can see that half-inch tubing would give us a conductance of 8.4 cubic meters per hour or 5 CFM. So what that means is that the maximum amount of gas I could get through a half-inch tubing of 1 meter length, so 100 centimeters at a pressure of 500 microns, would be 8.4 cubic meters per hour. And what that means is if I had a vacuum pump that's say 200 cubic meters per hour connected up with this really small diameter tubing, I've effectively wasted most of my pump speed because I'm only going to get a net pumping performance of something around 8.4 cubic meters. Obviously, if I had a 200 cubic meter per hour pump, I'm going to be looking at something like 1.5 inch, or we call NW40 tubing, 40 millimeters, 1.5 inch diameter. And that gives me sufficient pumping speed that I'm not going to suffer too much of a loss when I connect that up to my vacuum system. So I mentioned the impact of conductance on our pumping speed. This is what the formula looks like there. Obviously, it looks very much like our conductance formula did. but we can factor in the conductance of our aperture. Again, think about conductance as the restriction of gas moving through a tubing, and essentially it's like a cost. It's almost like a tax on our pumping speed that costs us our pumping speed. The way to calculate this is that our net pumping speed has to be calculated by the product of our total conductance, so adding up each of those individual conductances, and then multiplying that by our speed of our vacuum pumps and dividing it by the sum of those two things. So for example, if I had a conductance of 200 meters cube per hour and a pumping speed of 200 meters cube per hour, the ratio between those would be 1 to 1. And by doing this math here, I would get about half my pumping speed. So I'm going to lose 50% of my net pumping speed, just the fact on that restriction, because my conductance was on the same scale as my pumping speed. Down at the bottom of the table here, you can see if I could get to 10 to 1, so if my conductance was 10 times bigger than my pumping speed, I can recover 91% of my net pumping speed. And that's kind of the goal that we want to try for. There's no point in spending a lot of money on vacuum pumps and then giving it all up to conductance restrictions. So here's an illustration of a typical high vacuum system. As we worked through this with the paneling, it was interesting how many more elements we added that we realized that a system would typically have, for example, a high vacuum pump gauge, so we can verify the performance when the isolation valve to our high vacuum system is closed off, and verifying the net performance of our high vacuum pumping system. One of the things in particular that we in the vacuum group really like to have on the systems is the 4-line gauge shown here at number 8 in the picture. We spend so much time trying to troubleshoot high vacuum systems, and the problem ultimately results in some sort of deficiency in the rough vacuum side of the equation. So I know I hate to be advocating customers would add an extra gauge to their system, but we find so many times when we get to customer sites that we get led down a path of trying to troubleshoot a high vacuum problem when the net result could have been solved by simply having a 4-line gauge and being able to understand what the performance of our 4-line pumps was, be able to make sure that they were working fine before we got into the deeper elements of troubleshooting the high vacuum components. So speaking of which, let's talk about some of our vacuum gauges that we would use in a rough vacuum environment and also in a high vacuum environment, because obviously there's no single gauge that can cover the entire spectrum, if you will, of vacuum pressures. And that's, again, based on that physics that I described earlier. That boundary between viscous flow and molecular flow means that the technologies that we use for measuring rough vacuum can't really be applied to lower vacuum pressures. So most of the gauges used in industrial processes are of the thermal type. So these all exploit the relationship between heat loss through convection and vacuum pressure. And I always kind of think about this as like birds on a wire. So if I have a filament here heated up to 120 degrees Celsius, something around 250, I think that would be in Fahrenheit, every time gas molecules will hit that wire and leave, they'll take some amount of the energy with it. And we can exploit that in 3 different ways. Our least expensive gauges are the thermocouple gauges. So it's directly measuring the temperature. So this is the simplest gauge we would make. We would simply look at a drop in the temperature of that wire from its sort of set value here of 120 C as particles would land on it and take away a certain amount of heat. Now, those of you in the audience that have done experiments using temperature as your main parameter know that that's a relatively slow process. So we typically have some delay, particularly when there's big changes in vacuum pressure, for that gauge to respond, simply because there's a finite time that it would take the temperature change to be realized and recorded. Convection gauges put a little bit of a different spin on that, and what they're doing is trying to maintain the wire at a constant temperature and then monitoring the amount of current I have to put back in to replace heat loss to those gas molecules striking the surface and leaving it. One of the things we're going to need to consider with all our thermal gauges here is that just like up in our cartoon here, we have helium atoms and xenon ions hitting that filament, is that these gauges are going to be gas dependent. And that's because different gas species will take away different amounts of heat. For example, an argon ion will take away a different amount of heat than a nitrogen or an air molecule hitting that surface and leaving and taking away some of the heat. So we can see some of the benefits here. So these are going to measure typically from atmosphere down to about 1 millitorr. And again, there's a little bit faster response in the convection gauge based on how that mechanism works of measuring current rather than temperature. Kind of the top of the food chain in our thermal gauges is the Pirani gauge, and this uses a little bit different explanation, and I hope I'll try not to embarrass myself with any electrical engineers in the audience, but this uses a Wheatstone bridge circuit. And the way I understand this is that, that one of the legs, or one of the filaments, or sorry, one of the legs of the Wheatstone bridge will be our filament inside the vacuum chamber. And as heat is lost, the resistance of that filament will change, and the Wheatstone bridge essentially becomes unbalanced. And I always kind of think about like a teeter-totter here, and we need to apply a voltage to rebalance the bridge. Now, voltage is going to be directly proportional to the change in resistance of the filament, which is directly proportional to the heat loss, which again is going to be a measure of the gas density or the pressure inside a vessel. You can see here that on the graph in the bottom right of your screen, that the lines for different gas species all follow, they track pretty well. They have some offset, which is why we can apply a correction factor. We also need to be aware that up near atmosphere and the upper right-hand corner of that screen is all those lines start to diverge. So we need to be careful using Pirani gauges up near atmosphere, because there will be a larger degree of uncertainty in the measurement as we get up to atmosphere. When we get down to lower pressures below 1 millitorr, unfortunately, there's our thermal gauges all have to be replaced, because we simply don't have enough molecules there to be taking away any measurable amount of heat from that filament. So we move to a different technology, and what we're going to do is we're going to form ions inside our chamber. We're going to form positive ions, these M+ ions that we're showing here in the little graphic, and we're going to have a high negative voltage. Those ions are going to be attracted towards that negative voltage. If we get enough of those hitting the surface, we can actually measure a finite current. And that current, of course, would be proportional to the gas density inside our chamber or inside our vacuum gauge. And that, of course, will be a direct measurement or an indirect measurement of the vacuum pressure. Most common gauge used in industrial process is the cold cathode or inverted magnetron design. So these are variations on the same technology. I'm really proud of this one. This was invented by the Varian brothers back in the late, I think the 1940s, 1950s, somewhere around that time frame. And also this, in a serendipity incident, this led to the creation of the sputter ion gauge at the same time. So their first iteration of this gauge didn't work very well as a gauge, but turned out to be a fantastic vacuum pump. So the reason this is the most common gauge used in industrial applications is the fact that it's rugged. The filament gauge that we saw on the previous couple of slides ago really isn't as robust as this gauge, and a lot of our customers would see either deposition on the filament that would cause it to oxidize, and you'd see filament failure, or just the brittleness of that filament could become a problem. So cold cathodes, inverted magnetrons tend to be the choice for our industrial processes. One thing to note when I describe the process of doing this, there seems like there's a lot of interpretation there, and that's part of the cause of the accuracy of this gauge being plus or minus 50% over the vacuum range. So we need to be aware that we have much less ability to accurately measure vacuum pressures than we did in the rough vacuum space. So just a quick note on the nomenclature, the difference between the inverted magnetron gauge shown at the left here and the original cold cathode design. So there was changes made, and this was done way back in the 1960s. In fact, I think the first moon landing had an inverted magnetron style gauge. Inverted means that the polarity of the anode and the cathode have been flipped. So here we're using a grounded cathode to attract ions created at a much higher voltage. We also have sort of a more closed cylinder. You can see in the illustration on the left there that has better contains the plasma. But to me, the biggest difference is we increase that sort of strike voltage that we're going to use to create and maintain the plasma inside this from 2 kilovolts to 4 kilovolts. When I mentioned plasma, this is how we're creating those free electrons you see in the graphic up at the top of your screen. A plasma is simply a high energy field that has a collection of free electrons and positively charged ions. The fact that we have a magnet around the outside of this means that those free electrons will spiral around infinitely until they strike a background gas molecule. By doing that, we create those M positive ions, have those attracted to the negative cathode, and then we count those as a current, as I described earlier. I mentioned the fact that these are rebuildable. This is probably the most forgiving gauge that we have in our vacuum range. And again, these can be taken apart. They're largely mechanical parts. There's some replacement parts. I think the anode itself in this design can be replaced in a rebuild kit, but you're really using mechanical processes like Scotch-Brite and things like that, some chemical rinsing, and then drying, put it all back together, very simple to do, and then put it back into service. So gauge controllers, we have really two types of gauges. The thermal gauges I described earlier are mostly of the inactive type, which means that they need something to convert the output signal, whether it's the temperature from a thermocouple gauge, the current from a convection gauge, or the voltage from a Pirani gauge, convert that back into a vacuum pressure. So typically you could plug one of those into a vacuum gauge controller, and that would do a couple of things. Again, convert the gauge output as an electrical signal into a pressure. We can also display multiple gauges on a single controller, which gives us some benefits there. I'm not paying for displays at each single location. And also I can use this to have IO points and trigger set points. So we can take advantage there of reading that gauge signal in a controller and using that to set or to trip relays on our IO connector and use those in other parts of our industrial process. Active gauges are a little bit more sophisticated. These come with onboard electronics, and they'll have all the electronics. Some cases they'll even have their own display on them, that they're actually making the conversion from an electrical signal into a vacuum reading. So in a lot of cases, we simply plug in a simple wire. You can see the one on the left. I think both these have the actual, I think it's an RG59 connector that can be plugged into our system control and simply be extracting a vacuum pressure, reading that directly without any conversion, and then making decisions based on that through our IO. Okay, we've talked about how to measure rough vacuum pressures. Let's talk about how we can generate those pressures. So we can see you have a wide range of options. Some of these aren't typically used in industrial processes. So let's simplify our life a little bit and focus on probably the four dominant technologies. So we have rotary vane pumps, rotary piston pumps, screw pumps, and finally the booster blower package that we'll talk about as well. The tried and true rotary vane pumps, this is probably the most common type of pump that we'd see in industrial applications. I'm showing a real small version here. This is a DS602, something on the scale of 30 meters cubed per hour, but it's nice to show the illustrations here. The features will all be fairly common to different vacuum pumps, even if the packaging looks quite different. So we've got an oil inlet and an inlet vacuum port. These are very clearly marked on these pumps to avoid any confusion. Exhaust port, so we're going to need to take care of our exhaust in industrial applications, typically where there's a large flow where we're pumping down from atmosphere. We want to take care because that flow of air going through that is going to have a certain mechanical capability to take oil out of the pump, and we need to deal with that oil mist in some ways, typically going up in some sort of ventilation or a filtration system. Speaking of oil, we have a sight glass window here that we can monitor both the level of oil and the condition of oil. And one of the common causes of failure of this type of pump is that the oil gets degraded through exposure to the customer's process gas and will either deteriorate and form particles inside it, which can have the impact of blocking some of the jets inside this, or sorry, the journals that are lubricating different bearings and things like that. But also just straight deterioration of the oil will also deteriorate the vacuum performance of this pump. It's something we need to consider. One of the features that almost all rotary vane pumps have is the gas ballast shown on the screen here. And that's a mechanism that we can use if we're pumping large amounts of water vapor. What you'll see through that sight glass is that the oil itself will become contaminated with water vapor. And that shows up in a couple of ways. The oil will look a little bit sort of milky and will also have some sort of bubbles in it, kind of like maybe a sort of a ginger ale look, if I can use that analogy. And opening the gas ballast on a dual stage pump like we see here will allow a little bit of air to flow directly into that second high compression stage of the pump, and that'll generate a fair amount of heat. And what we want to do there is get that water back into vapor phase and have it be pumped out the exhaust along with the process gas traveling through the pump. And running that gas ballast on a pump like this, typically for something like half an hour, has almost a miraculous effect of cleaning up the water vapor from the oil. A quick illustration here for anyone who's not familiar with the rotary vane pumps, how these work. Our gases are in viscous flow, so all we really need to do is create at the right-hand side of the cartoon here a pressure that's lower than atmosphere, and our particles, through those collisions with each other, those remember those bouncing balls around in the circle, they're going to find their way into this pump. I seal them off when that rotor is just about horizontal. I seal off a little sort of crescent-shaped volume of gas, and then I move that into a smaller and smaller volume such that the pressure goes above atmospheric pressure, and then the little exhaust valve will open and that gas will, of course, burp out into the room. And that's why you hear that sort of popping sound when you first turn on a vacuum pump, rotary vane pump from atmospheres. You're hearing that exhaust valve open and close. In a lot of applications, customers will be using a dual stage pump. In that case, the exhaust of the first system, shown in red here on your screen, instead of going out to atmosphere, will go into a second chamber, typically a smaller chamber with a little bit tighter tolerances, and that's performing a compression effect and compress gas even higher. By doing that, that allows us to get to much lower vacuum pumps, although a lot of our industrial customers don't really need to get down to the 10 to the minus 3 torr in their primary pumps. Some advantages and disadvantages. I won't read off these one at a time, but you can see these. And again, a slightly different configuration, maybe something a little bit more common to our industrial customers in the sort of look and architecture of a single stage, in this case, rotary vane pump. Rotary piston pump, this is the sort of tried and true, and I would say a large percentage of the industrial customers we would go into would be using one of these style of rotary piston pumps. I love the mechanism on this. It's much easier to show this cartoon than try and describe it in any kind of words here. Knock against these, of course, would be it's probably the loudest thing. In fact, one of our panelists commented, when you go to almost any industrial plant, the loudest thing in that plant will be the rotary piston pump. Fair amount of vibration generated. These will almost dance across the floor if they're not bolted down adequately. Advantages is, of course, ruggedness and rebuildability. We're seeing a lot of these in applications that could be 10 or 20 years old, perhaps even older than that. The screw pumps, these are common a lot in industrial customers that have sort of a very aggressive process that might be attacking different metal surfaces, might prefer to use the screw design. One of the things to note that there's a couple of varieties of these. We can have oil sealed or dry variants, and we can have screw pumps that act as a booster pump, and that would be a fixed pitch screw here. So picture just having two mechanical screws turning together. We could imagine there's a little spiral pathway for gas to move along. Variable pitch ones here, as you can see those two rotors on the far left of your screen, that would be moving gas into a smaller and smaller volume and giving us a compression effect. And that would be the type of pump that would operate on its own and ideally can generate enough compression to exhaust gas out at atmospheric pressures. So the ability to pump down from atmosphere and get to a pressure somewhere probably around 10 to the minus 1, possibly into 10 to the minus 2 torr. Okay, I mentioned the booster blower packages here. I'm going to focus on a single stage blower rather than some of the newer multi-stage designs that we're seeing recently. We've got a schematic of the two vacuum systems. Of course, over here on your right, you can see the addition just above typically a single stage vane pump would be our roots blower package here. And the main advantage of that is that we would get significant pumping speed from something like 1 torr, 10 torr down to our crossover pressure to our high vacuum system. And what that translates to is directly the time it takes to get to our crossover pressure where we can engage our high vacuum pumping system, whether that's a diffusion pump, in some cases a turbo pump, or possibly even a cryo pump. So we can imagine this vacuum chamber being pumped along at something less than 100 liters per second, as opposed to this one, which transitions to a booster package. And now we're getting pump speed in the 400 liter a second range before we hand off to our high vacuum system at 650 liters per second. So you see that we have a significant time advantage in this one because we were maintaining our pumping speed for much lower in the pressure regime. So I would say that the large percentage of customers where time is a factor are going to be employing that booster on top of a mechanical pump. There's some very special cases or that comes into play when we talk about leak detection that John McLaren will get to in a few minutes. We're going to talk about vapor jet or diffusion pumps. Personally, I prefer the name vapor jet. since the mechanism of pumping here is used to be thought to be diffusion of gas molecules into a stream of pumping fluid. And now I think it's really more considered that this is the pumping effect is happening through momentum transfer. In fact, again, one of my colleagues mentioned recently that Mars Sublanian, one of the godfathers of the vacuum business, was actually petitioning the American Vacuum Society to change the name from diffusion pumps to vapor jet pumps. So he certainly got my vote in that case. So let's talk about these in some detail. They're the most common high vacuum pump that we're going to see in industrial applications. And let's go through some of the different aspects. And in particular, we're going to talk about maintenance and troubleshooting once we get through how does this pump actually work. So as I said, the pumping mechanism is largely thought to be through momentum transfer. So those large molecular weight oil molecules are going to be ejected from a station. These kids should probably be playing inside the vacuum pump here, but I thought that would be a fun little analogy of how diffusion pumps are working. Whereas this is working on gravity in the diffusion pump, that the equivalent of the chocolate here would be shooting out at very high rates of speed. The ejection speed of the pumping fluid is something like 750 miles an hour, 330 meters per second. The reason we try and achieve that really high speed, because that's the speed the particles are moving at room temperature. It's kind of a bat and baseball analogy. It's much easier to hit something moving at 750 miles an hour if the oil molecule is traveling at that speed itself. Of course, our oil molecules are much, much bigger in mass, so perhaps hundreds of times bigger in mass than the gas we're trying to pump, the small diameter nitrogens and oxygens and things like that. So the momentum impact is huge. When one of those oil molecules hits that, it's going to be knocked out towards the edges of the pump and knocked down through the different stages, kind of like we see the different stages in this chocolate factory here. All right, system design and operation. We could do a lot of background slides on this, but I wanted to try and simplify it as much as possible. Really, there's two stages of operation. Typically, industrial processes, we're talking about large volume chambers. So we need to use this kind of bypass process where we have a holding pump that's keeping our high vacuum pump shown over here on the left. And we're going to engage our high vacuum pump, typically a diffusion pump. We're going to have its exhaust be pumped away by a small holding pump here. And we're going to use our large diameter booster blower package here to be able to evacuate our chamber down to what we're calling the crossover pressure. When we hit our crossover pressure, we're going to open up this valve here. And we're going to allow the pumping pathway to happen along this way. So we're going to use our large capacity booster blower package as the backing pump for our turbo pump at this point. So that's why when we talk about vapor jet or diffusion pumps, once we get into operation here, it's typically not a concern that we're going to exceed the 4-line pressure because we've got such huge pumping capacity based on this booster connected to a single stage, typically rotary vane pump. So I mentioned in the slide we talked about our gas loads. We're going to talk about backstreaming, but really more in the case of how do we try and minimize the amount of oil vapor going back into our system. So the fact that this is a pump that's shooting out oil mist at very high speeds means it's inevitable that we're going to have some of our vapor that goes back into our vacuum system. So some of the ways we can minimize that is maintaining the 4-line well below our critical backing pressure. As I mentioned earlier, that's not so much of a problem once we're in fully operational and we're using our large vacuum system that we use to rough the chamber with as our backing pump. Typically, we've got plenty of capacity there. Selecting an appropriate crossover pressure is much more complex and is also much more unique to each individual system. And what we'll find is that what we want to do is we want to be able to engage our high vacuum pumping system, our diffusion pumping, as early as possible, but we need to be aware of how long it's going to take for it to be operating well within its sort of comfort zone or its sweet spot. Wherever we're operating that pump above its an inlet pressure that it's comfortable with, we're going to have that potential for oil mist going back. We're going to start to see a breakdown of those jet cones coming out from of mist coming out from the different stages. So most common way to mitigate oil mist going back to our chamber is the use of cold traps. We can also have an extended cold traps, water-cooled baffles, or LN2 traps. And for each of those, we get a greater and greater reduction in the amount of oil backstreaming. The trade-off with each of those in order from cold cap through to LM2 traps is the amount of restriction they place on our vacuum system and how much they compromise our pumping speed. Remember back to our discussion about conductance. Anytime we put something in a line of sight baffle, it's going to have some ability to reduce those particles in random motion molecular flow from finding their way in to our diffusion pump, where they can be captured by those different jet stages and eventually pumped out the exhaust. Soft opening inlet valves is another common technique that our customers will use, where they can essentially crack a valve a little bit on our high vacuum valve, letting a little bit of gas go over, letting the high vacuum pump do its job to very quickly reduce the vacuum pressure, such that when that valve's fully open, there's not so much of a net inrush of gas molecules that might have the ability, or might have the consequence of collapsing those vapor jets. Cooling water is very critical in diffusion pumps. We need to maintain that the water is connected correctly, where the inlet and the exhaust of water are connected appropriately, and also that the temperature and flow are within the specifications for the individual pump and the type of oil that we're using. Speaking of oil, we need to choose appropriate pumping fluids based on our vacuum performance that we require, but also based on what kind of backstreaming we can tolerate, and also what our chemical process, what we're actually going to be pumping away as a pumped media. As we know, the different gas species that we're trying to pump could break down the fluids in different ways. So we need to take all those things into consideration. Careful venting and shutdown. There's things like cold loops inside some of these pumps that will rapidly cool down the oil when they're turned off. And we want to try and, once we've stopped pumping, we want to try and get that oil to cool and go back into 100% liquid phase as quickly as possible. The less time that gas spends in vapor phase, the less chance there is of oil molecules wandering their way back up and perhaps contaminating our vacuum system. And finally, proper maintenance. One of the main things, one of my favorite customers to go to is the maintenance guys that keep really good records on these diffusion pumps. So they've characterized them, let's say at the start or installation, or when they've done a maintenance, and they can track the behavior of it. And that allows them to schedule regular maintenance and appropriately schedule their downtime, and really try and avoid unplanned downtime, which of course is a real problem for our industrial customers. I'm just going to briefly on one of these very old Varian technical reports. This is VR175, and it describes some specific steps that customers could take to try and mitigate the effect of incoming gas stream on those gas jets. So it doesn't look like that file is going to open. But I'll tell you what, if any of the audience members want a copy of that report, we can send that out separately under separate cover. Simply use the email at the end of these slides. Okay, so let's talk about maintenance for a second here. I'll try and keep the screen a little bit clean and being conscious of the time as well. So when we're looking at maintenance, we're looking at for the vacuum fluid or the pumping fluid. Sometimes I refer to it as pumping oil, although there are different species that can be used. We need to maintain the fluid level inside the pump. Obviously, the lower the fluid level, the more problems we're going to see with the pump. We can see overheating. We can see sort of destruction of the fluid through overheating and, let's say, cracking of some of those hydrocarbon fluids. And if we are losing fluid in our pump over time, we need to troubleshoot the cause. Maybe the exhaust baffle isn't put in properly. Changes in color of the fluid may indicate exposure to high inlet pressure or some sort of a breakdown mechanism, depending on what gas species we're pumping. We need to be aware of crystallized pump. I've come across this a few times in using diff pumps. Is that in the boiler section of the pump that we're going to see almost like granules or crystallized oil, and that can indicate problems with the cooling water. We want to make sure that the water is not too hot and not too cold, and also, as I said earlier, maintain the appropriate flow rates. Fluid contamination I described may require some sort of chemical analysis, and maybe there's a different choice of pump fluid that can help us that would be more appropriate for a particular gas process. Cooling, as I said, cooling water, 60 to 80 degrees Fahrenheit inlet, 100 to 125 on the exhaust, and we need to maintain the flow rate. And different pumps from different manufacturers will have different specifications on what that flow rate would be. And we need to make sure that that flow is maintained within that. We need to be aware of a couple of things that companies using city water or cooling towers, that can change drastically in the temperature of our source water from different seasons. And also we need to take care of what the mineral content of our cooling water is. If we're using water, I may need to use some sort of a descaling agent, depending on where our water is coming from, whether it's well water or city water. Also a note here on glycol coolants, they don't absorb as much heat as water does, and I think we have to take that into account when we're considering the cooling and the performance of our diffusion pumps. Maintenance logs, I can't say enough about customers that do routine maintenance on us and keep track of the behavior of their pumps over time. These are the easiest guys to work with when it comes to troubleshooting when we go into a customer site to try and understand if something's not quite working right with their chemical process. We can look at that historical data and look at the degradation, let's say, in performance, and that gives us a much better lead on where to start looking for problems. Typically, pumps are dismantled from the system, taken apart and cleaned. When putting them back together, you want to make sure that the jets are aligned, and also that, in particular, that the ejector stage is in line with the exhaust or the foreline of the pump. We've seen that in different cases. And when we're cleaning, there's a couple of different schools of thought. There's use of solvents and abrasive pads, and just plain elbow grease, getting in there with some sort of abrasive steel wool or emery cloth, something like that, and cleaning up the surface of those jets. Bead blasting is pretty common, although we need to be careful not to distort the shape of the jets, because that's going to influence what the shape of that cone of high velocity oil mist coming out of the pump is going to look like. And any breakdowns in that are going to create, let's say, a leak path for gas molecules to go back towards my chamber. Recently, I've talked with our colleagues in the customer call center here, and they've mentioned some of the customers are using dry ice blasting as a sort of an inert way of doing that bead blasting without the potential for damaging the mechanical surface of the jets, but also it has the benefit that nothing ever stays in the liquid phase, that these will sublimate back directly back into gas phase. And I'd really like to follow up on that. If anybody in our audience today is using dry ice blasting to clean up jets, I appreciate if you could drop me a line and give me some input on that, because I'd really like to incorporate it into our future training sessions. Finally, the heaters, since this is a process that requires heat to boil the oil or to vaporize the oil so that that jet stream can form, we need to make sure that the load is balanced on three-phase circuits and that the total wattage is appropriate for the heater style that we have. If the load's not balanced, we want to measure the resistance of each heater with the power off and look for any faults or shorts in that system. Heater plates need to be torqued to specifications in order to optimize the heat transfer from the heaters themselves to the bottom of the boiler. Again, the boiler plate should be flat and smooth. Some of the Agilent design pumps use a crush plate to ensure that we have good thermal contact there. And all electrical connections need to be tight and properly crimped. One of the things that we'll recommend is that customers will use pure nickel versus nickel or copper plated lugs and wires in the construction of the electrical connections to a diffusion pump. Finally, we're going to get to vacuum fluids. I'm just going to talk a little bit about this. We could do an entire webinar just on vapor jet fluids. So I'm going to talk just a little bit about it. We show here in this graph, this is right from Agilent's catalog. We're still showing the Dow Corning 704 for reference only here, just so that we can look at the relative parameters here. Things that we really care about are going to be the ultimate pressure, the vapor pressure, and the boiling point. And those are things we're going to look at. Typically, there's going to be all high molecular weight compounds. I think on the screen here, you could imagine going from the left to the right. Sanovac, some of you that may be using that, very expensive as a pumping fluid. Really, I guess one of the things that I want to get across here is that there's no universal fluid, and the choice of fluids is going to really depend on what you're trying to pump and what your requirements are and what you need to achieve as a vacuum process, and also what kind of maintenance cycle you're going to be on and things like that. One of the things, since Dow Corning's kind of dropped out of this market, is that there's a lot of different sources of fluid, and I want you to make sure that you're sourcing your fluids from a reputable supplier so that you can get the same thing week in, week out, and know that you've got a process that you can adjust and optimize with a particular fluid, and be able to have that process be repeatable. There's nothing worse than getting another batch of fluid that doesn't behave exactly like the one previously. There's an alternate 704 that our guys in our factory in Boston had looked at and evaluated against Dow Corning 704 and found it was pretty close, but not exactly the same as the DC 704 was. So again, you really need to be careful, and I can't stress enough to choose fluids from a reputable supplier. Finally, there's a troubleshooting guide that we put together. We got all the applications guys, Dave from our industrial marketing team, and Kenny in our call center, and went through this line by line and tried to come up with the most common probable causes for different faults you might see with the diffusion pump. And rather than go through this line by line, what I'd like to do is offer it up to our customers. We'll put this with a nice letterhead on it, and we can send it out to you as probably a PDF file. So anybody who wants, you can simply email our customer care group at the Agilent email below here, and we'll send you out a copy of these. There's 2 pages of it. Again, I don't think that there's time to go through each of these line by line, but we're happy to share this with you, and we're happy to take your feedback on any things that you find that could supplement this troubleshooting guide for us. Okay, that's a lot of talking in a hurry. I hope that was useful for you. Right now, I'd like to hand it back to Vicki, and we're going to hear from John McLaren as we talk about how we would specifically use a helium leak detector to troubleshoot industrial vacuum systems. Thanks very much. We'll talk to you at the QA.
All right, excellent. Thanks, John. This is John McLaren. I'll pick it up from here, and we'll talk about leak testing some of these large chambers. Again, we are getting close to the end, so I'll go at a fairly quick pace here, and hopefully get a few tips and tricks along to you about leak testing a vacuum chamber. So the first thing is recognizing, if you actually have a leak or is there some other problem, and then following that, once you've determined you have a leak, what are some best practices or some tips and tricks that you can follow that make testing a little bit easier? And then finally, much the same as John did, I'll highlight some online resources that we'll make available to you that might serve as a good follow-on reading material. So when you pump down a vacuum chamber, you're probably going to get something that looks like one of the 3 curves that you see on the screen right now that indicate, what is the condition of my system. The normal pump down, you get down to a base pressure within a certain amount of time. Without gassing, you might sort of get there, but you take a lot longer. And then with a leak, you just get down to a certain point and you can't get any further. So how do we identify the difference between a real leak and outgassing or a virtual leak? So a real leak is going to look something like this, where you pump down to a certain point and then you're going to monitor the rate of rise in the system. What is the change in pressure versus time? So in this first plot, you see our pressure rising at a fairly steady rate, the blue line. The yellow line is our rate of rise, how many microns or how many, what is the measurement per hour or per minute that we're seeing in that change. The difference with outgassing or a virtual leak, as you can see, is even though the pressure is coming up, the rate of change of that pressure changes with respect to that pressure. So in this case, you see that that rate of rise actually decreases as the pressure increases. And this is either due to the fact that the leak is a limited leak like a virtual leak, or it's an outgassing leak and there's less outgassing at a higher pressure. So once you've determined that you've got a real leak, now you've got to actually then decide that, okay, I've got to leak test my system. So you understand the difference in your rate of change in these 2 systems. So when you do this pressure rise, okay, you've got a lot of limitations. One, it's slow. You've got to pump it down, take the time to do that, and you've got to wait for that pressure to come up. Temperature variability can cause that pressure to vary as well. So we know that pressure and temperature go hand in hand. So changes in temperature are going to give us some problems. We're going to have very limited sensitivity. Typically, pressure decay doesn't allow us very sensitive leak testing. And of course, the most obvious thing, it won't tell you where the leak is. You're not going to be able to pinpoint the leak. So leak testing with helium is a great way to figure out where the problems are in our vacuum system. So here I've got just a representative system similar to what John was showing you earlier, where we've got a high vacuum chamber connected to a diffusion pump and then a roots blower and mechanical pump package. We're going to spray helium around the outside of it, and we're going to look for a leak in this system. The first thing you need to determine is, where do I connect my leak detector? And I've got 3 possible places here I've outlined. You might think it's obvious I should connect to what I think might be leaking, and that's my chamber. But the problem is we're not going to take advantage of our high vacuum chamber in this case. So instead, we want to connect to the 4 line of the high vacuum pump. That allows us to take advantage of the vacuum pump's performance. It gives us the fastest response time, the fastest cleanup of our helium signal. It gives us the absolute best sensitivity. I do caution people to stay away from the region between your roots blower and mechanical pump. It's susceptible to a little bit more contamination, and mechanical pumps aren't great pumps for helium, so you can get what's called helium backstreaming, or essentially a high helium signal that just won't go away. A couple other tips on helium and how to use it. You want to make sure you optimize the flow of helium from your spray probe. If you stick your spray probe into a glass of water, you just want to see a couple of bubbles a second coming out of that probe. You don't want to hear that helium coming out. If it sounds like a compressed air line, you're spraying way too much helium. And what that's going to do is cause problems with background helium. You're essentially polluting the entire environment that you're trying to test in, and that background signal is going to give you some problems. It's going to mean it's harder to clean up if you find a gross leak, because now again you've got an elevated level of helium in the area where you're trying to test. Spraying too much helium also can mean you're not sure where exactly the leak is. You could be spraying in one area but have so much helium in the room that it's triggering other leaks to indicate as well. So when you're leak testing your system, you want to start at the top, work your way down. If there's a lot of air movement, you might want to consider starting at the pumps first and then working your way out away from the pumps. And then there's a couple of shielding techniques you can use as well. You can shield other fittings with some type of a barrier, a plastic bag, a rubber glove, something like that, where you're spraying on another fitting. Or kind of the reverse of that, you can actually wrap tape or a plastic bag around a particular flange or fitting and then squirt helium underneath that bag or that tape, and you're just going to check that joint alone to see if there's a leak in the joint. Now, on a leak detector, zeroing is something we always get a lot of questions about, and I'll very quickly go through what we mean by zeroing helium background. It's something that can save you a tremendous amount of time when you're leak testing a large chamber, and that's because when we bring our leak detector in and we connect it in the right location, and then this is what our display looks like on the detector, and we start spraying helium, over time, our helium level is going to increase. And you see now we've come up off our baseline reading of the leak detector. We're indicating we've got a leak in the 10 to the minus 8 range. But the inside of our chamber is becoming polluted with helium. There's a low level of helium in there, and it can take some time to pump that helium away. So what we do instead is we're going to come in and we're going to press the 0 button on our instrument. So now you see our detection level goes back down to the most sensitive level. This means we can continue testing. We haven't lost any sensitivity. We've just reestablished our 0 reference point on the leak detector. So when we do that, we just want to make sure we're spraying a minimal amount of helium, and we always want to make sure that you don't hit the 0 button at the same time you're spraying helium. That can mean you might miss a leak. But as long as you follow those rules, being able to zero that signal and reestablish your baseline can save you a lot of time. You're not waiting for all that helium to be cleaned up and pumped away. You can continue testing. So when you zero, you can utilize a function on our instrument called an auto zero less than 0 that allows that baseline to be reestablished, and it won't lose any sensitivity. It means you can keep testing. It's going to compensate as that background helium inside your chamber cleans up, and you don't lose any accuracy or sensitivity on the instrument at all. As I say here, we've got a white paper that explains this subject in great detail. There's a link to it at the end of the presentation, and it can give you a lot of tips on how to best use zero in your application. If you've got such a large system that you're having to move away from the leak detector and you can't always monitor what's going on the display, a wireless remote is always a good idea. This way you can carry the remote with you. You can see how the leak detector is responding and monitor the leak rate as you're spraying helium around the system. I've been in facilities where you're up on a mezzanine at the top of a large vacuum chamber spraying helium. You can't see or hear the leak detector, but with the remote, you can still track what's going on. So to summarize the key points here, make sure you utilize the high vacuum pump on the system when at all possible and connect to the 4-line of that high vacuum pump. Keep your helium flow to a minimum. Otherwise, you're going to just create more trouble and more problems for yourself. And use the zero function to save time. You can save a lot of time by not having to wait for that helium to always be cleaning up, and using the wireless remote if necessary for a large system. So I mentioned we've got a lot of links here. You can see several of them here. Again, we'll have a recording of this presentation distributed, so you can get those, or if you would like, you can also email us, and we're happy to distribute this information to you directly. So thank you very much for your time, and I know we're right at the limit here, but maybe we've still got some time for questions, or again, you can utilize the email to follow up with us, any of us, on any questions that you have. So thanks very much, and I'll turn it back over to Vicki for any questions.
Thank you, John. Thank both of you for that excellent presentation. As you mentioned, we are up at the top of the hour here, so we won't be able to get to some of the questions that you asked, that the audience has asked, but please know that you'll be contacted in a few days by one of your panelists. I encourage everyone now to complete the brief survey that will appear on your screen as you exit the webinar. With your input, we can continue to provide webinars with high quality, practical information that you can use. I encourage you to follow up with our presenters for more information on vacuum for your industrial process. Once again, I'd like to acknowledge the sponsor of today's webinar, Agilent Technologies. Learn more about how Agilent's products and services can make a measurable difference to your business by visiting their website found on the screen. Thank you again, everybody, for participating in this ASM webinar. Have a great day.